Hey everybody, in today's lesson we're learning about a new type of probability distribution called hypergeometric distributions. So let's get started. I have a motivation problem for you. This is a problem that we are able to do after our last unit on organized counting involving committees and therefore combinations. So I've scaffolded this problem for you. First, we're interested in finding the probability that in a committee of 5 people from this group of 20, where 12 are female, what's the probability that our committee will have 3 females? So if you think about 12 out of 20 is 60%, 3 out of 5 is 60% too. So we're kind of thinking about what's the probability that the ratio of females in our small committee is the same as the big group. And I've scaffolded this problem for you guys. So to do part C, set this up a little bit over here. To do part C, to know the probability of having 3 females in your group of 5, you need to find the number of ways to get 3 females on a committee and the number of total possible committees, which is the number of elements in our sample space here, to get that probability. So I'm going to leave that with you guys if you want to pause the video and give those a try. So I've basically set up C. You have to do part A for the numerator, part B for the denominator, put those together. When you're ready, you can unpause and we'll take it up. So yeah, let's proceed. I have this question done on my next slide already. So the number of committees that can be chosen, there's 20 people. We are selecting a committee of 5. Order does not matter. That's just 20 choose 5. But 15,504. For part B, to have exactly 3 females. So of our 12 females, we have to choose 3 of them. 12 choose 3. And to round out the committee of 5, of the remaining 8 males, to make 5 in the committee, you need 2 more males. There's 8 choose 2 ways to do that. And the fundamental counting principle says we would multiply those 2 results together. And I got 6,160 different committees that can have 3 females exactly. And now you can finish off part C, the number of ways to get 3 females, the total number of committees, and you can divide those. I got almost 40%, 39.73%. This question could almost be framed as a binomial distribution question, almost. Because if you think about it, we've really got like 5 trials, right? We're just selecting people for our committee. So you can think of that as like 5 people being chosen, 5 trials. But the reason this differs from a binomial distribution is that every time you pick a person, the probability of selecting a female changes because there's 1 less person. Whereas with the binomial distribution, the probability of a success in any given trial was the same. The trials were independent of each other. In this case, every time you take a person, that changes the probabilities that the trials are dependent. So a very similar problem to a binomial distribution problem, except the trials are dependent here and not independent. So any type of problem where we're selecting some objects from one group, I call this like a success group, and some objects from another group, which I often refer to as a failure group, and finding these probabilities can be classified using what we call a hypergeometric distribution. So in these cases, the trials are dependent. So that is the big difference between this distribution and the binomial distribution. Whoops, binomial is not spelled with an O, at least not there. So unlike the binomial distribution, trials are dependent. There are 2 possible outcomes for each trial, success and failure. That is similar to the binomial distribution. And so in our example there, a success was getting a female on the committee and a failure was getting a male. Note that we could easily have flip-flopped that around. And the probability of success changes as each trial is made. So like we hit in the previous question, once somebody's picked for a committee, they can't be picked again. There's 1 less person and the probabilities change. Some more notes. These are on your lesson sheet. So just like binomial distributions, the random variable is the number of successful trials. So in our example, it was the number of females on the committee. The calculations generally require combinations, and this calculation calculates the probability of a specific number of successes in a given number of dependent trials. So this may look like a lot, but this calculation, you guys did one of these earlier. You have 3 combinations to calculate. So I'm going to circle. So this guy in the bottom, I'm going to say this is the just kind of like the total amount of groups. So if you have n items and you're choosing a certain number of items, so in our particular problem with the committee, the total number of items was 20, and we were choosing 5 people for our committee, 5 items, so R was equal to 5. And you'll notice in our calculation we did earlier, on the bottom, we had 20 choose 5, 15,504. On the top, you've got 2 combinations. You have kind of what I call the success group. In this case, it was the number of females. And in this calculation, so N is the total number of items, R is the total number of items being chosen, or the trials, and the last variable is A. This is the number of items in the group we're looking at, or the success group, and in this case, it was the number of females. And in our example, A was equal to 12. So there's a few more parameters going on, but every hypergeometric distribution calculation is just 3 combinations: your success group, your not success group or failure group, and on the bottom, the total number of groups. So it looks like a lot, but it's just 3 combinations. And and with these 3 parameters, N, R, and A, our random variable is the number of successes. And when you look at this combination, like the second one, and if you're intimidated by all the subtraction and all the variables, just think like if we had, remember we had 20 people, if 12 of them were female, then 20 minus 12 would be in our failure group. And so notice that these 2 numbers are always, these 2 guys here will always add to the bottom. And if we had, if we had our items being chosen, or like our people being chosen for a committee, if X of them are a success, then the difference has to be failures, and those always add up to the number of trials. So as we do calculations later, a little self-check to make sure you're setting them up right, so that all these left numbers in the combinations add up and all the right numbers in the combinations add up. Let's talk about the expected value for a hypergeometric distribution, because we can get it the standard way by looking at all the possible outcomes and their probabilities and using the expected value formula, multiplying outcomes times probabilities, adding them up. But the hypergeometric distribution has kind of an intuitive formula that we can talk about right now. So because if you're choosing, we had 20 people and we're choosing a group, if you did it randomly, you normally expect, you had a certain percentage of females in the population. If you're choosing a random committee, you kind of expect that you have the same proportion of females in your little subgroup there. So as I write this out, I'm going to frame it in terms of the example we just did. So let's say the expected number of females on our committee, if you take that ratio divided by the total number of people in the group, it should match the original population where we had 12 females. So that's the number of people in our success group divided by the total number of people, 20. So as I get this in a general sense, maybe below it, we'll do it with our specific example. So let's say you wanted to find an expected number of females in a group. Well, we were choosing 5 people for a committee. In general, 12 of the 20 were female, and these ratios, we expect them to stay the same. And now to solve that proportion, we just multiply up the 5. 5 times 12 divided by 20, which is 60 over 20, which is 3. In general, to get the expected value, you just multiply up this R, and you get this formula, R times A divided by N. And so you can see intuitively why it works. The ratio of the expected number to number of trials, R, is proportional to the number of available successes, which in our case was 12, over the size of the population, which is N. So this formula will always be given to you, but yeah, it's a nice intuitive formula that you can use instead of having to multiply outcomes and probabilities. It's nice to have that. So let's do an example. So suppose we select 5 cards without replacement from an ordinary deck of playing cards. What's the probability of getting exactly 2 red cards? So let's think of what our parameters are. And notice that we are not replacing the cards. If we were replacing the cards, then we can do this question using the binomial distribution, because if you keep putting the cards back, the probability of getting a red card isn't going to change. But since we're not replacing, trials are dependent. This is a hypergeometric distribution question. So let's talk about our variables. So we have a deck of playing cards. That's 52 total cards in general. We are selecting 5 cards. The number of trials is 5. And we are focusing on getting red cards. That's our kind of our success. The number of possible successes is 26. There are 26 red cards in the deck. And so having done that, we can now set up our probability. So let's do it. What's the probability of getting exactly 2 red cards? This might not be a necessary step for you guys, but I'm just going to to remind you, we're just using theoretical probability here. All right, let's set this up. So let's set up this hypergeometric distribution calculation. And remember, it's just 3 combinations. On the bottom, what's the number of possible 5-card hands? Well, it's 52, choose 5, right? It's N, choose R. And on the top, we have our success group, A. We had 26 red cards. And we're choosing, by the number of ways to choose 2 of them. And then we have our failure group, the black cards. So remember, these left and right numbers always add up. If you have 26 red cards, you have 26 black cards, adds 52. And to get exactly 2 red cards, that means we have 3 black cards. And look, 2 plus 3 is equal to 5. So we've set up this calculation. They all look the same. And now we just have to find out what the answer is. 26 choose 2 times 26 choose 3 divided by 52 choose 5. And in general, with these kind of questions, I usually go to 4 decimal places as a decimal, and then 2 decimal places as a percentage. So about 32.5% likely when you deal out 5 cards to have exactly 2 red cards. Let's do this. Look at this example from a different direction. So suppose the game has changed. So even if we get 2 or fewer red cards, so what's the probability of winning now? So the probability of winning, we're looking for the probability. So to get a win, that involves getting 2 red cards, but we could also win if we get fewer than that. So also 1 red card, or also no red cards. So 3 calculations to do here and adding them up. Note that in this question, it's probably easier to do this directly. 2 red cards, 1 red card, 0 red cards. Actually, maybe not easier. Actually, I think there's one less calculation, because you could also do, so you lose if you get 3, 4, or 5, right? So you could take 1 minus the probability of getting 3 red plus 4 red plus 5 red. So either one of these situations involves 3 hypergeometric calculations, but in this one, you would subtract from 1. But if the question was like 4 or fewer red cards, then certainly the indirect method would be faster. But here, let's do it this way. So we've actually already done 2 red cards, right? So we had 26 red cards, choosing 2, 26 black cards, choosing 3, all over 52, choose 5. Why don't you guys take a moment, if you want to pause the video, and try setting up the calculation for 1 red card and 0 red cards. And then you can unpause when you're ready. Here we go. So in the second calculation, our success group is 1 red card, which means we have 4 black cards. And the denominator here is always 52, choose 5. Again, the left and right numbers always add up to each other. And then finally, we have no red cards, which means all 5 cards must be black. 26, choose 5, over 52, choose 5. So for this one, you may want to do each one individually. We got 0.3251 the last time for 2 red cards. My advice would be to do each calculation separately and then add those up. But if you feel comfortable, there's no reason why you couldn't just do everything at once. Let me do things one at a time though. So for getting 1 red card, I got 0.1496. And for the final one, 26 choose 0 is just 1. So you can just kind of ignore it if you want. 26 choose 5, divided by 52 choose 5. So this one I got 0.0253. And so we win if either of those is true. So we'll add up those guys. Plus 0.0253. So, sorry, that's just my kids. So we get exactly 0.5, which actually makes sense because there's 3 cases where we win, 2 reds, 1 red, 0 red. And there's 3 cases where we lose, 3 red, 4 red, 5 red. And because they're exactly the same amount of red cards and black cards in a deck, it actually makes sense that we got 0.5 or 50%. Let's look at another example. So maybe try this one on your own. So we have a box containing 7 yellow, 3 green, 4 purple, and 6 red candies jumbled together. We are going to get a handful of 10 and find the probability of getting exactly 3 red candies. So I'd like you guys to try it. What you need to identify is, your 3 parameters. What's N, what's R, and what's A. And then you guys are looking for the probability of getting 3 red candies. So red candies is kind of like our success. So again, you can pause, try it, unpause when you're ready, or follow along with me. But let's begin. So what's N? Well, how many candies are in our little jar here? 7, 3, 4, and 6. That's 20 candies altogether. And we're pouring out a handful of 10. So a number of trials is 10. Our success group is red candies, and we have 6 of them, 6 available successes for us. This particular question wants the probability of getting 3 successes, 3 reds. We can do it. So we'll set up our calculation. So the number of ways to pour out 10 candies, 20 choose 10. So N choose R on the bottom. 2 more calculations up top. We have our success group, red candies. We want 3 red candies. So of our 6 red candies, we're choosing 3 of them. And of the remaining, remember these add up to 20, 14 other candies, we are choosing 7 because they have to add up to 10. Hard part was setting it up. Easy part now is we can just do the calculation. So 6 choose 3 times 14 choose 7 divided by 20 choose 10. So in this case, you're about 37% likely to have this happen. So 30.3715 or 37.15%. So another example in the books. Hopefully you're getting more comfortable setting up these calculations. Let's find the expected value of red candies. So remember, things kind of stay proportional. So if you think, 6 of 10 red candy, 6 of 20 actually, which is 30% of the candies are red. When you pour out 10, 30% of those should be red too. Well, 30% of 10 is 3. So when I'm doing my expected value calculation, I'm expecting to get 3. So let's see if this happens. So our expected value formula, which we can just use all the time now, R times A over N. So we were pouring out 10 candies. 6 of them were red. And there were 20 altogether. Gives us 3. Our expected value is 3 red candies. We expect 3 red candies when we pour out 10 in this example here. All right. What I'd like you guys to do now is I'd like you guys to try to create a distribution table. So if we, and these parameters correspond to our motivation problem with the committee of 5 people, where we were looking at getting a female as a success. There are 6 possible outcomes for you guys. You could get 0 females on the committee. You could get 1, 2, 3, 4, or 5. And I believe we've already done the 3. So 0 females, 1 female, 2 female, 3 female. You guys can use that. We've done it already, or you can redo it if you'd like. But you guys have 6 hypergeometric calculations to set up. Remember, the check is that if you did it correctly, if you've got all the outcomes, their probability should add up to 1. So give that a try, make sure they add up to 1. Keep 4 decimal places, and then try the expected value on your own. Now, we did kind of do it earlier. I used it as an example, kind of improvise that. So it kind of spoiled the fun a little bit. But yeah, if you want to get that here, what's the expected value of females? And if you want, you can double check that with multiplying x times p at x and adding them all up, but that will take a while. But yeah, just use a specific formula. So you can pause the video and try that. I've got solutions kind of done already for the next slide, so you can go there when you're ready. I'm going to go there right now. So you can see I've set up my 6 calculations. I got 0.3973, which is what we did earlier in our motivation problem. But now we just did it for all the possible outcomes. And I checked. Mine added up to exactly 1. Remember, if you're doing a table and you're having to round, it may add up to like 0.9999 or a little over 1 just because of rounding. But here it gave me exactly 1, so that was good. And again, the expected value for n equals 20, a equals 12, r equals 5 was we expect to get 3 women, which was what we saw earlier. All right, the last kind of question I want to do with you guys is an interesting application to biology, ecology, whatever you want to call it. I'm not a biology expert. I stopped taking biology in grade 11. Just was not for me. All the memorization and whatnot, I just could not handle it. But this is kind of how tagging works. So if you want to get information and estimate the size of a population, it's impossible to, like, in this case, it's seals. It's literally impossible to, in a particular colony in an area, just count up all the seals. You don't know whether you counted the same one twice. You don't know if some are missing, some are swimming underwater. So what we do is we take a sample. So in this question, we took a sample of 350 seals, and we tagged them. So 350 of these seals will have a tag. And then later on, maybe several years later or what have you, these scientists go back and they caught 40 seals, and they looked at how many had been tagged. 17 of them have been tagged. So 17 of the 40 seals were tagged that they caught. And they know that 350 seals out of this whole colony are tagged too. So we can use these proportions and expected value to find the size of the seal colony. So let me get a few things down here. In this question, what we don't know is the population of the seal colony. What we do know is that the number of successful or number of tagged animals is 350. We took a sample of 40 seals, R equals 40, and 17 of them have been tagged. We're going to use that as our expected value. So I might set this one up two ways. We'll see actually. So remember we talked about when we derive this expected value. The expected value over the sample size should be proportional to the number of successes in the population. So A over N is the number of successes in the population. E at X is like what we expect the number of successes to be in the sample size. And here it's tagged animals. And we know 3 of those 4 things. So in our problem, we know 17 is the tagged number of seals out of our 40 that were tagged. 350 were tagged, and we're looking for N. And we can solve this proportion using whatever method you like. I like using cross multiplication. So we do 40 times 350 and divide by the third number, 17. So we can estimate the number of seals in the population. 40 times 350 divided by 17. So we get about 823.53. So remember, this is just like a EDX was a predicted average. If you in a case like this, if you can't have half a seal, it's totally fine to round. Not a big deal if you don't round as well. But we could guess there's about 824 seals in this population. So that's how tagging works. And the way to estimate the population actually involves the hypergeometric distribution and its expected value. So that was a fun little example, in my opinion. Next steps for you guys. So just really quickly, as we are doing distance learning at this point, I am definitely trying to not overwhelm with practice, yet still give people enough practice to, master the concept or, work ahead or do more if they'd like. So my students that have their textbook, these questions are from 178. I will say too, the key concepts, usually each chapter has the summary of the key concepts. They're never a bad idea just to copy out into your notes. A lot of times I teach from this resource and my key concepts are kind of the same, but sometimes I word things a bit differently that work for me, and maybe having a different voice or different wording can sometimes help a concept sink in. And then I've got some questions for you guys to try. Video solutions will be posted. Yeah, please reach out if you need anything. Thanks for keeping up your learning and watching this video. Hope you guys have a great day. We'll see you soon.